Welcome back. So, we're in the middle of the section of the course on dynamics, and the specific part of that dynamics section having to do with chemical transformation, which is, part and parcel of the nature of the living world. Things get converted into other molecules, get converted into other molecules all the time as a matter of course. And in the previous vignette, what we did was we laid out the, more than century old treatment of enzymes, which is known as Michaelis-Menten kinetics. And as I pointed out, this is but a small fraction of the way that one can think of enzymes. And let me just make a plug for the idea of allosteric enzymes. These are enzymes that can be controlled by some other molecule, which can change their state of activity. And there's a paper that you can find on my website by Tal Einav, Einav, in which we kind of review not only Michaelis-Menten, but allosteric enzymes as well. So what I want to do here is I want to talk about some recent calculations that we did in preparation for the third edition of our book. This was primarily driven by Christina Heshin, and what I want to say is that this was inspired by a beautiful paper that was written by this collection of guys. So Hinz Peter, Uli Gerlin, and Tosteven, and I wanted, I just gave a little side vignette about the literature and my bad job of keeping up with trying to acknowledge where things have come from. So we were inspired by this paper. We didn't end up actually following it per se, but we were very inspired by it. So here's the idea. What I want to do is I want to talk about a question, and the question is one of compartmentalization. So the schematic shown here in the upper right illustrates two coupled enzymes where enzyme 1 consumes a substrate which produces a product which we were going to call an intermediate, because that intermediate is the substrate for enzyme number 2. And the question that we're going to ask is there any advantage to putting all of this stuff in a compartment? And I can give you the intuition right from the get-go, and then we'll do some calculations that sort of provide a foundation for that intuition. So the intuition is that if I only had enzyme E1 and the exterior to the compartment was where I had, let me call it S0 or S infinity, which is the substrate concentration is held fixed outside, then the substrate has to get across the compartment membrane or shell, and then it will be acted upon by the enzyme number 1. And the larger I make the compartment, the harder it will be for the surface. This goes back to the surface to volume ratio thing that we did at the very beginning of the course. It will be harder for the surface to feed the interior volume. And at some point, the surface will not be able to keep up with the volume consumption of the enzyme. And that's what's shown basically here. So this curve right here is the concentration of substrate inside of the compartment, and this curve is the efficiency, if you like, per enzyme in the model that I just described. This is a single enzyme model. In other words, I'm not thinking for the moment about the enzyme number 2. I'm just saying if I have a single enzyme and I compartmentalize it, it will do worse than if I just left it in free space. And the reason is because I will not be able to keep up with delivering material to the inside of the compartment. But now here's the rub. This is the fun part. If I put in the second enzyme and there is no intermediate on the outside, then the larger I make the radius in this case, the harder it is for the intermediate to escape. And so there's going to be some optimal point at which the substrate loss is bad, but the intermediate preservation is becoming so good because I've sent the surface far away that surface to volume fight for substrate and intermediate actually leads to an optimal radius. And that's what's shown here, which is this thing. So this peak corresponds to the case in which the ultimate product formation is served better by compartmentalizing than by leaving the two enzymes uncompartmentalized in the exterior medium. So what we're going to do is we're going to try to consider this, this situation and try to understand it from a somewhat quantitative point of view. So for the moment, let's just think about this case, which which is that I have a compartment, and the external world is held at a substrate concentration S0. Okay, so I have a reservoir, is the way I want you to think of it. I have a reservoir of substrate in the external world. I have some compartment, and these molecules can cross this surface, and they do so according to the law of permeability, which I show you right here. Okay, so what does this say? So this thing says that there's a quantity known as the permeability, and what I want you to see is that it has units of length per second. So this is length per time. And then this is the concentration difference. So the delta C, concentration difference across the surface. And then this is the area. So you can see that the net result is that this thing has units of number per time. So it's a rate. So just to reiterate, what I'm telling you is that if I have a membrane, so here's a membrane, and on this side I have a bunch of molecules, and on this side I have none, there's going to be a flux across this membrane, and that flux is going to be given by P times delta C. So it's a little bit different than Fick's law because we don't divide by a length. It's not delta C by delta X, it's just delta C. So permeability times the concentration difference gives us a flux, okay? So what I'm doing in this equation is I'm basically balancing, as you can see. On the left-hand side, this is the rate of consumption of substrate on the interior. Let's just look at this. So E1 is the enzyme concentration. This is the volume. So that enzyme concentration times the volume tells me the number of enzymes. This is the rate per enzyme. And then this is the Michaelis-Menten form that we worked out in the previous vignette. It's telling me that the enzyme will increase, the amount of product formation will increase with increasing substrate concentration until we reach saturation. The saturation occurs for S much larger than K. At that point, where K is the Michaelis constant. So what I'm doing in this equation is I'm balancing, on the one hand, the enzyme action on the interior and the delivery of substrate to the interior by the surface. And that's due to the gradient or the change in concentration across the surface. So really what I'm saying is that in steady state, the production of product is balanced by the rate at which substrate arrives on the scene. And so we can basically rewrite what I wrote above in this form, okay? And you'll notice that, if you take kcat, which has units of 1 over seconds, if you take enzyme concentration, which is number per meter cubed, and then the permeability, which is meters per second, then 3 ps over kcat has units of R. So this R and this R cancel each other out, and I'm basically left with this simple form for the balance across the surface and in the volume. So this thing actually leads to a quadratic equation. What I'm trying to find is the substrate concentration on the interior. Why do I care about the substrate concentration on the interior? Because as we already said, the rate of product formation, which is the thing I really care about, is this. This is the rate of product formation, and it's given by this Michaelis-Menten form. Okay, so I need to find the substrate concentration on the interior, and to do so, I basically multiply both sides by S plus K in this equation. That yields this, which is a quadratic equation, and I can solve that quadratic equation as you see here, and that tells me the substrate concentration on the interior. This is assuming no spatial effect. When I say spatial effect, what I mean is that the diffusion, once the substrate's on the interior, is so fast that I can think of the substrate concentration on the interior as effectively uniform. So that model is what's plotted here, right here. So this is the substrate concentration on the interior, as a function of the radius of the compartment. So as I said at the beginning, no matter how small I make the compartment, it does not matter. The concentration on the interior is always going to be smaller than the concentration on the exterior. So this reaction is always going to go slower than it would if the enzyme were in bulk. But now let's think about part 2 to this, which is the intermediate reaction. So now what I'm doing is I'm saying, well, look, on the left-hand side, this is the rate at which I produce intermediate. Remember, when I have the double enzyme problem, I have E1 and E2, what does E1 do? It produces intermediate. How fast? This fast. Why? Because substrate is this thing, and this net equation gives me the total rate of production of intermediate. On the right-hand side, what I have is the rate of product formation plus the rate of loss of intermediate across the surface. Okay? So once again, I'm doing a steady state balance. On the left-hand side, I'm saying this is the rate at which I make intermediate. On the right-hand side, I'm saying this is the rate at which I lose intermediate. There's two processes whereby I lose intermediate. Either I lose it because intermediate gets converted into product, that's what I want, or alternatively, I lose it because it permeates across the compartment membrane and is lost, and therefore not available for making product. So I balance these two things. Now note, S of R is a parameter at this point. I've already solved for this. It's the previous calculation. I know S of R, so it's a parameter. What I'm trying to find now is I of R. I want to know how much intermediate there is, and then I will be able to use that intermediate through this expression to figure out the rate of product formation. So once again, we have a quadratic equation. Why? Because if I multiply by I plus K2 here, then there will no longer be any i's in the denominator, and that will lead to this kind of messy quadratic equation, which you see right here. If I solve that quadratic equation, sorry, it's kind of messy. That's the reason I wrote it ahead of time, because I didn't want to make any algebraic mistakes. I think this is right. And although I can't even really read my own writing, I don't it's terrible. Like this thing is confusing. That must be an I. Let me fix that. So this tells me the intermediate concentration as a function of the radius. And that's what's shown right here. This is awesome. So what do we learn? We learn that there's an optimal radius at which the amount of intermediate is maximal. So in other words, it not compartmentalizing means that the ultimate productivity of our enzyme product formation will be lower than if we actually compartmentalize. Why? Because when we compartmentalize, we set up this interesting competition. We compromise the substrate. In other words, there's less substrate available than there was in the external medium. But the advantage of that is that the compartmentalized substrate leads to compartmentalized intermediate. And when I start making the radius larger and larger and larger, I start actually keeping the intermediate such that it doesn't leak away into the reservoir. So now the second enzyme is able to actually churn out more product. So what I'm telling you is that this result is showing us the amount of intermediate as a function of the radius of the compartment, and this curve is showing us the rate of product formation per enzyme as a function of the radius of the compartment. And so once again, what we see is there's an optimal radius at which we will get the most bang for our buck out of this coupled enzyme system. So just to summarize, the intuition was that we started with a question, which is, well, first of all, we have an observation, as you remember from the carboxysome case, for example, and we know this in the context of nitrogen fixation and other things as well. We know that there are localizations of enzymes, and so that leads to a physics question, if you like, a quantitative question, which is, does the system somehow work better by virtue of this compartmentalization? And for this toy model, which I think is a good toy model, actually, we see that there is an advantage to being compartmentalized. So I'm sure that I'll give the students in the course an opportunity to play around with this model a little bit more in a homework problem. hopefully this introduction gives you a feel for how this compartmentalization idea works.